If you place a biological cell into a highly concentrated, high-salt environment, it quickly shrivels and shrinks. To understand the physical mechanics behind this biological process, we must isolate the core variables. This YouTube apparatus provides a clean look at the system. On the left, pure solvent. On the right, a solute mixture. At the bottom, a physical barrier. This barrier is a semipermeable membrane. While it looks solid from a macro perspective, zooming in reveals a wall filled with microscopic pores. Small molecules, like our pure solvent, are exactly the right size to slip through the gaps, but the dissolved solute molecules on the right are physically too large. When they collide with the membrane, they simply bounce off, unable to cross into the pure solvent. Because the heavy solute molecules take up space on the right side, fewer solvent molecules hit that side of the membrane to cross back. This creates a net movement of pure solvent molecules flowing strictly from left to right. This specific directional flow is osmosis. Osmosis is a strict mechanical drive toward equilibrium, powered entirely by concentration differences across a porous barrier. Left completely alone, this flow of solvent continues until the system balances itself out and reaches a natural resting state. But we can intervene before equilibrium is reached. By applying an external mechanical force to the solution side, using a physical piston, we can push back against the incoming solvent and halt the rising liquid level. The exact minimum pressure required to completely stop the flow of osmosis is called osmotic pressure, represented by the Greek letter pi. Osmotic pressure is a colligative property. This means its strength depends entirely on the total quantity of dissolved particles present in the solution. Colligative properties are blind to the identity of the substance. Whether a dissolved particle is a complex sugar molecule or a simple ion of salt, its physical effect on the pressure is identical. Because this pressure only registers quantity, measuring pi gives us a direct, highly accurate tool for counting invisible solute particles in a solution. For dilute solutions, this physical relationship translates into a clean mathematical equation, pi equals CRT. The critical variable here is C, which stands for molarity, the total concentration of the solution. Mathematically, molarity breaks down into the number of moles of solute, represented by N2, divided by the total volume of the solution, V. The remaining components are standard constants. R is the universal gas constant, and T is the absolute temperature measured in Kelvin. If you hold the temperature and the volume constant, the equation reveals a simple, linear relationship. The osmotic pressure rises and falls in exact proportion to the number of dissolved particles. Historically, chemists utilized this precise proportional relationship to weigh microscopic molecules they could never physically see in a laboratory. We know that the moles of a dissolved solute, N2, can be found by taking its known physical mass, W2, and dividing it by its unknown molar mass, M2. By substituting this into our formula, we can isolate M2 on one side of the equation. Molar mass now equals the known mass times RT, divided by the osmotic pressure and volume. Because osmotic pressure is measured at room temperature, it remains a primary method for determining the mass of large biomolecules, complex proteins, and polymers. However, this formula represents an ideal state. It relies on one absolute assumption, that every individual molecule you dissolve remains exactly one intact particle once it enters the solvent. Physical reality frequently breaks this ideal mathematical model because certain solutes are structurally unstable when submerged in a liquid. The first anomaly is dissociation. Take a standard ionic compound like potassium chloride. When it enters the solvent, the ionic bonds immediately break. A single molecule of KCl splits into separate potassium and chloride ions. This means if a chemist theoretically dissolves exactly 1 mole of KCl, they are actually flooding the system with 2 active moles of particles. The exact opposite anomaly is association. If you place ethanoic acid into a solvent like benzene, the behavior reverses. Instead of breaking apart, the separate ethanoic acid molecules lock together through hydrogen bonds, forming a rigid, combined structure known as a dimer. Now, 2 originally distinct molecules move and act as a single, heavier unit. The number of independent particles in the solvent drops by half. Because osmotic pressure is governed entirely by the physical particle count, these invisible structural changes silently corrupt the pressures we actually measure in the lab. When we compare the theoretical prediction of the equation against the physical data coming out of the laboratory, we see a stark mathematical paradox. In the case of dissociation, the extra dissolved particles drive the osmotic pressure unexpectedly high. When plugged back into our equation, the calculated molar mass appears falsely low. With association, the reduced particle count lowers the osmotic pressure. The math then concludes that the molar mass of the solute has artificially doubled. When the experimentally determined mass drastically deviates from the expected normal value of the molecule, it is classified as an abnormal molar mass. This is not a calculation error by the chemist. It is a mathematical failure to account for the dynamic, hidden physical state of the molecule. To resolve this paradox, the scientific community needed a mathematical bridge. In 1880, chemist Jacobus Henricus van Hoff provided the exact correction factor required. He introduced the van Hoff factor, the variable I. It is calculated by taking the observed experimental property and dividing by the calculated ideal property. Physically, I equals the moles present after dissociation or association divided by the initial moles dissolved. This gives us a clear diagnostic metric. If I is greater than 1, the solute is actively dissociating. For a compound like KCl, I is approximately 2. If I is less than 1, the solute is associating. Ethanoic acid joining into dimers yields an I value of approximately 0.5. And if I equals exactly 1, the solute is perfectly stable, remaining intact as it dissolves. The I factor calculates the reality tax of the solution. It quantifies exactly how far the physical system has deviated from the perfect mathematical model. By surgically inserting the van Hoff factor into our ideal osmotic pressure equation, we instantly correct for math to reflect reality. This discrepancy is rooted in particle count, making it a universal disruption that alters every colligative property in the system. We apply the exact same correction to the boiling point elevation formula, and we apply it again to the equation for freezing point depression. By universally integrating the van Hoff factor, we construct a robust thermodynamic framework capable of handling perfectly ideal substances and chaotic reactive solutes. Colligative properties are governed strictly by the sheer number of particles, completely blind to the identity of the elements involved. Abnormal molar masses are entirely the result of solutes undergoing hidden structural transformations that warp that fundamental quantity. The van Hoff factor serves as an investigative tool, decoding the dynamic behavior of unseen molecules. To master physical chemistry, one must bridge the gap between elegant mathematical theory and the messy physical reality of the particles themselves.